Okay, so let's walk through these homework solutions. When you look at number 10, really what we're looking at is first diagnosing the form. When I see this, I see it as something times something else. So its form is going to be the product rule. So I write stuff times stuff. So it's going to end up being the first times the derivative of the second plus the second times the derivative of the first. And when you simplify all that out, you get negative sine squared plus cosine squared. When you look at number 12, to know what tool to pick up, I have to recognize the form. So its form is stuff divided by stuff. So that means it's going to be low d high minus high d low over low gets squared. So derivative of cosine is negative sine. Derivative of negative sine is negative cosine. But then we distribute here and get this. We distribute here and get plus sine squared. Then cosine and cosine, if they're both negative, multiply together to get positive cosine. But I have this very important fact memorized, that sine squared plus cosine squared is always 1. So this is just equal to 1. But I had this minus sine left over out in front. So then I really have this over this, but I can rewrite it as this times what's left over. But since that's just equal to 1, you just get this. All right, so that's 12. Let's look at 16. So 16, you can view it as this multiplied by this, because when you have three things broken up, you can use the associative rule, the associative property of multiplication, to associate the first two together and let the last one hang out by itself. So its form is stuff times stuff. So that means it's going to be first derivative second plus second derivative first. And so now the derivative of cotangent is negative cosecant squared. Then I have a derivative inside here. Its form is stuff times stuff. So its derivative is going to be inside of here. First derivative second plus second derivative of first. So it's like a derivative within a little derivative, right? So then when we differentiate this, we get this. And then I distribute this through and get all this and just leave this chilling. 26, it asks for the equation of a tangent line, so I automatically write down this. And then it tells me at this point, so I write down that. So that means I can plug in my y1, and my x1. But then to find m, it's just the derivative at your point, so it's the derivative at pi over 3. But if I take the derivative, I'm going to get this. So when you plug in pi over 3, it's just going to be 3 minus 6 sine of pi over 3. But we know that the sine of pi over 3 is square root 3 over 2. These cancel out and leave me with a 3. So my slope is just this, and you plug it in. And so really, you could be done at this step. The rest of it is just possible simplification. I would be okay with what's in blue. 36. It tells us that we have a, what's this, a mass on a spring, looks like this. So if you take its first derivative, you get velocity. And if you take its second derivative, you get acceleration. Then there's a Desmos link on Canvas because it asks you to graph those suckers. So when I go to Desmos and look at that graph that we had, if we click on just the first one, it shows the acceleration graph. It wants to know, when does the mass pass through equilibrium for the first time? Well, I guess it would be right here. When I click on it, it shows me that it's about 2.55 seconds. Then it says, how far does the mass pass? How far from equilibrium does it ever travel? Really, it's just asking the amplitude, and so that would be 3.6 approximately, right? Then it says, when is the speed the greatest? Well, then we're really looking at velocity, which is this red graph. It looks like it's the greatest right here. And interestingly, notice it's the greatest when it passes through equilibrium, which is something super interesting to think about. Is it always going to happen that way? Why does it make sense? But that's a great question. So next, that is, what was that? That was 36. Then when we look at 40, we're really leveraging these limit ideas that we had before. So, let me go back here. So, if I have this, I know that the limit as x goes, as x goes to 0, why does it keep on doing that? Of sine over sine, sine x over x is just equal to 1. And so if I can get it to look like this, I'm going to be able to do good work. So I wish this had a pi in it. So to do that, I have to multiply it by a well-chosen 1, pi over pi. And so when I do that, I am going to put one of these pi's on bottom. And so if I multiply it by pi over pi, the pi on the bottom, I'm going to put with this x that's, oh, actually, excuse me, I'm going to multiply top and bottom by pi x over pi x. So my pi x on top, I'm going to put over sine pi x, because I know that's going to go to 1. And then I put my pi x underneath sine x, because I know that this is going to go to 1. So I have this little pi that's hanging out. I can pull it through because it's a constant. It's really 1 over pi. So I pull that out to the front, and then I have two limits I can solve. The limit is x goes to 0 of this, and x goes to 0 of this, because the limit of the product is the product of the limits as long as they exist. But I wish this was just one variable, so I let theta equal pi x. I just give it a name and say, let that be a variable by itself. And the good thing is, as x goes to 0, theta is also going to go to 0. So really, this stuff here in yellow can be replaced with its equivalent version in terms of theta right below it. So then this is a constant. This goes to 1, and this goes to 1. So when you multiply these together, you get 1 over pi. So that's 40, and then 42 is the penultimate question. So I'll just show you the one on bottom. This is the way the textbook did it. I did it differently up top, which you can see. But the second version that they did, they just said, look, when I look at this, well, first when you let epsilon go to 0, you get 0 over 0, so you've got to change the form. Well, an easy way to do it is to use this well-chosen 1, because I wish that this was cosine of theta minus 1 over theta, and I wish this was sine of theta over theta. So by having those limits memorized, that this goes to 0 and this goes to 1, I can look through those things I have memorized, and it helps me to do this problem. So I recall that those are true. And so now when I multiply by 1 over theta, this theta I put underneath here, and this theta I put underneath here. But the limit of a quotient is just the quotient of two limits as long as the limits exist, and they do. Because the top one just wants to be 0, bottom wants to be 1. 0 divided by 1 is 0. 48. I wish this was the sign of something over the same thing, so I guess I have to multiply x on bottom, but if I do, I also have to do it on the top, so I need to multiply by a well-chosen 1, which is x over x. Now you might say, oh no, you're multiplying by 0 over 0. You're not. X is approaching 0. It never actually reaches 0. So we're just multiplying by something really small over really small, which is completely legit. So then I take, and this x times this x gives me x squared on the bottom. So again, this x and this x, which was already there, give me this x squared, which is on the bottom. And then I now have the limit as x goes to 0 of x times another thing. So this is the limit of a product. I can write it as the product of two limits as long as those limits exist. Well, guess what? This is just wanting to be 0. And this, what happens is, I'm going to let x squared be theta so it's easier to see. And if theta is equal to x squared, I can rewrite it as the limit as theta goes to 0 of the sine of theta over theta. Because as x goes to 0, is it clear that theta also goes to 0? So I write this in its equivalent form. And so that thing right here in red wants to be 1. And so 1 times 0 is 0. And we're done. So great job on the homework, and I will see you next time. Expect a review in the coming days. We'll have a review day next time as well. Have a good one.